Oh, perfect. If it's on your side, then it's perfect. All right. I'm glad that all the AV issues have been resolved. So, for those who haven't seen my talk before, hi everyone. And so my name is Wojciech Różowski, and normally I'm a PhD candidate at University College London, where I'm working more on the theoretical side of programming language semantics. But right now, I would like to talk about something very informal, more hand wavy, but also more practical. And I like to think of this as a some sort of an opinion talk or some sort of a um, uh, some sort of almost like a video essay or pointing out one interesting thing. So this is a joint work with George and Sean, who were mentoring me during my Amazon internship 2 summers ago. So yeah, let's crack in. So Dafny offers amazing levels of automation for being to be able to write programs and write contracts what they should do or what they shouldn't do, and then verify that those programs obey those contracts. And as we all probably know, it relies on encoding to the intermediate language being Boogie, and then generating verification conditions out of Boogie, which are logical formulae whose validity entails the correctness of the program, which leverages the opportunities of possibilities of SMT solvers such as Z3. And the main story of this talk is that as much as this automation is amazing and it's something that by default you would like to have, there are some cases where one might opt for more fine-grained approach. So I'll be talking about fine-grained approach to reasoning about some difficult, and I'll mention what kind of difficulty do I mean, Dafny programs using Lean Proof Assistant. So Lean is a theorem prover or a proof assistant, so some sort of a tool from a similar domain as Dafny, however, more centered towards mathematical proofs, more popular in the mathematical community, and it essentially allows one to develop proofs in this semi-manual conversational way, where in the IDE, which is form of Visual Studio Code with a plugin, one writes the proofs, and then while writing the proofs on the right-hand side, in the editor, one can see how different steps of the logical proof change the assumptions into conclusions of the proof. So rather than relying on automation by default, you are the one in charge of constructing the proof, but also you get this interactive experience of developing the proof. So if you were to compare these two guys, Dafny is first of all, they are from completely two domains. Dafny is mainly for program reasoning. It is aimed also for people outside of the usual domain of mathematics or type theory. It is a highly automated tool where, as much as people say they prove things, I like to think that you don't really prove things in Dafny, but you rather hint them to the SMT solver, which is the one that actually is doing the job, where Lean is a semi-manual tool where you are in charge of developing the tools, developing the proofs. Of course, there are some tools in the forms of tactics that allow you to resolve some kinds of goals, but it's more on the manual side. So let me motivate you why on earth one might want to reason about a Dafny program using Lean. So let's look at this very simple piece of code, which is a split function that takes a string, that takes a character and an integer, and it replies with a sequence type, so a list of strings. And the idea is that we take a string, which might contain some separator. We take a separator character and a number for which will specify the limit. And we're trying to split that string by that separator bounded by the limit. So for example, if you give this Sid, Nick, and Roger concatenated with a semicolon inside, and we ask to split it by semicolon, and we give the limit of 2, then we get Sid and then Nick and Roger, so 2 elements. We don't split these two guys. If we give it a negative number as a limit, and we give again the same string, so Sid, Nick, and Roger, and ask to split it by semicolon, we get those 3 members of early Pink Floyd as a separate elements of the list. All right, so this is how you might go about implementing it. So you could argue it's a fairly simple program. There is no mutable state. there is mutable state, but there is no heap reasoning or locality-based reasoning. You simply go through the string and you accumulate the segment you've seen so far. You keep going through the string, and if you see the separator, then at this point you cut the string. So namely, you take whatever you've accumulated so far, you push it to the working list, and you keep going. And once you're done with the loop, then you take all the remaining segment you might have accumulated until the end of the string, and you push it to the working list. The only interesting thing is this break statement. So the idea is that if we are about to hit the limit, if it's a non-negative limit, then we just stop traversing the string and we immediately go into just remembering the rest of the string. So let's say that we're trying to prove some specification of this code, try to show that this code adheres to some specification. So let's say we provide some precondition and postcondition and loop invariant. So this is how it would look like. Fair enough. So then let's say that you get a following error. Okay, a postcondition could not be proven on this return path. So you inspect the code, and you, as a Dafny user, you think, okay, we return something. There is a loop. Maybe the problem is with a loop invariant, because essentially this is the last thing you enforce before doing this last manipulation before returning. This could be a good hit. It could be an issue over there. However, there is one extra thing. Turns out that the problem might be on the branch that breaks out, where the invariant is not established. And this is something you might be aware of if you're a more skilled Dafny developer, that you know how it actually deals with non-local control flow. But the thing is, in your head, you're thinking about two different execution paths, and you're trying to construct two proofs with different set of assumptions. Because in one hand, you enforce the invariant and you just do this little manipulation with a finished variable. In the other one, you still have some there is a bit more assumptions on the way. So in a situation like this, I would like to argue that it would be really good to be able to visualize the proof state, not in order so you don't have to keep the mental model of what's going on, but rather you can rely on some sort of a external help saying what is true at a given point, what I'm trying to prove. So now I would like to talk about our proof of concept, how we went about this particular problem. And this is the tool that we've implemented. So we go from a Dafny program, and we extract a bunch of straight line programs that correspond to different possible program paths, and such that the correctness of those individual straight line programs will entail the correctness of the global program. And those straight line programs, are in a small boogie-like language. Therefore, I'll refer it to as microboogie. And in our case, microboogie is a data type implemented in a lean theorem prover that is equipped with a formal semantics and with formally verified verification condition generator, which spits out you the thing you have to prove using lean, that if you can prove, that means that it's correct with respect to the semantics. And this process of proof is something you do through the interactive semi-manual proof. So let me talk about the first bit of it, which is the extraction of the straight line programs. So we rely on this very neat result from Jean-Christophe Filiatre's paper on formal reasoning about mix programs. And mix is the language used by Knuth in his book, which is a very low-level programming language with non-local control flow. And very similar idea has been studied by Rustan and Mike Barrett, and in the case of Boogie. And the idea is that we construct a control flow graph of a program, which is annotated with preconditions, postconditions, and invariants. And such a graph contains three kinds of things. So contains white nodes, gray nodes, and edges, which might be annotated. And the idea is that white nodes represent the code that is being executed. Gray nodes lump the idea of precondition, postconditions, or invariants. Those are just predicates that should be true at a given point once you pass through them. And edges correspond to the control flow. And if there is a some sort of a Boolean formula on them, it means that you assume that if you take that edge, that thing is true. So you construct such a control flow graph, and then you extract all possible paths between any two gray nodes that do not contain any intermediate gray nodes. And you just concatenate the code contained on the white nodes, as well as the conditional, like the Boolean formulas on the conditional branches. And the idea is that the starting gray node is something you assume to be true, and the ending gray node is something you assert, you're trying to show that you would like to be true after executing the program. So you start with assuming the gray node you start from and asserting the one you end at. So let's look at an example. This is a very simple block which ends with a gray node and ends with a gray node. So we assume the precondition, we perform the initialization code, and then we assert the loop invariant. So essentially it means that we're trying to establish the loop invariant before entering the loop. This is how it would look like. Let's go back to the motivating problem. So this is the straight line program that corresponds to exiting the loop in the normal way. So you assume the loop invariant holds, you touch the finished variable, and you assert the postcondition. This is how the other branch stemming from the break statement should look like, where you assume the loop invariant holds, you navigate through the loop body in a way that you take the branch that might break out, and you try to assert the postcondition. So there are two completely different programs that once you prove, they deal with two different set of assumptions. So to deal with these guys in a interactive way, let me talk very briefly about encoding them in Lean. So here is the syntax of this micro-boogie language, where you can assign to variables whose identifiers are strings some sort of expressions, where you can put assume and assert statements. You have also non-deterministic choice statement, which allows you to model external function calls as well as you can sequentially compose programs. And the idea is that the semantics of such program is a relation between states, where a state is a mapping between the values of the identifiers of strings and the values they might take, which are some sort of a primitive data types like integers, naturals, booleans, characters, primitive lists. And we deal, so we've given semantics of these programs in Lean, as well as implemented the weakest precondition style generation of verification conditions, which essentially takes a predicate, which is a statement about the program, and unrolls the program and accumulates the things that needs to be proved, and generates generates a proof obligation that should be dealt in Lean through the semi-manual proof. So very quickly, to sum up, we've built a very simple prototype tool which supports a small fragment of Dafny', namely the one where you don't deal with heap reasoning, where you only deal with those very simple data types. And we've done a case study on string splitting. And the main lessons I've learned through this is that it was quite straightforward to develop the proofs once you had this level of visibility, that you know what is true at a given point, what you're aiming to prove. On the downside, because of the way it was encoded, there was a lot of sublemmas you had to prove that involve boilerplate properties, which weren't interesting, and you had to do with a manual proof. And this is something I really like, and that Dafny' can figure out automatically. And I envision that it will be difficult to build a solution that will target a full fragment of Dafny'. So what's the point, you might ask, of this whole thing? I like to think of this as some sort of starting debate, how and what would be the good way of improving the user experience of Dafny' if you would be like to be able to see the internal state of the proof. This is something that Rustan mentioned in his keynote about the IDE support. Like, can one add proof state to Dafny'? How one would go about this? I'm not trying to propose a full revolution to replace any part of Dafny' with Lean, but rather I would love to see similar things that Lean enables being part of Dafny'. The bigger question is, like, can one improve Dafny' support for reasoning about those non-local programs in making explicit this extraction of different paths, as this is what we've mentioned before, and quite orthogonally to this, how one can use proof assistance to discharge proof obligations for Dafny. And again, this is something that has been studied before. So, for example, Y3 or YML are intermediate language. Y3 is an intermediate language like Boogie, where you can deal with, you can rely on SMT solving, but you can also do this, resolve the proof obligations via Coq theorem prover. So one could think that maybe the problem I present is not really a problem with Dafny, but rather something that should be targeted at the level of the intermediate representations of the program, that they're encoded well enough so SMT solver can deal with them, but also they're encoded in a way that you can get meaningful proof obligations to deal with them manually. So here are the two main references I mentioned. So this paper of Jean-Christophe Filiat and Mike Barnett and Rustan Leino. And with that, I would like to wrap up, and as I would be more than happy to answer any questions you guys might have. Thank you very much for having me. I really regret I cannot be in person with you. So yeah.
Anyone?
I cannot hear anything, so I don't know if there are questions or not.
All right. Hello. Can you hear now?
Oh, yes. Okay. Yes, it works.
Thank you. Thank you for the talk. So I saw you had the data type that encoded like the assert and havoc and things like that. For your propositions, it looked like it was like a state to prop function. So how are you embedding the like logical part of Dafny into Lean?
That's an excellent question that I would love to elaborate more. So essentially, in the prototype tool we relied on the assertions being written in Lean rather than in Dafny immediately. And the idea was that we relied on the rich annotation system of Dafny, where you could reference Lean specification using attributes in the code. And essentially those were referencing the names of the mappings into prop in Lean. And the reason I done so is because being able to encode a full Dafny assertion language is something I find very difficult. One, because of the well-formatness conditions, such as, for example, conjunction is not commutative. This is a very nice example. It really relies on the ordering and on like how it interplays with well-formatness. Additionally, there is a very interesting interplay between some sort of a meta theory, that in one case you're dealing with a first order logic meta theory, in the other one you're dealing with this type theoretic meta theory. So I kind of avoided the problem. But again, I would love somehow the intermediate language where you can use to write the assertions to be flexible enough to both rely on SMT automation and something you could deal with the theorem prover. So yeah, this is an excellent question.
Thank you.
All right, let's thank Wojciech again.
Thank you.